So this lecture will look at two more amplifier configurations, the common source amplifier with source degeneration and then the common source amplifier with a diode connected load. We'll focus on the AC characteristics because we've already studied the DC characteristics earlier on. So here is the common source amplifier with a resistive load and a source degeneration, which means that there is a resistance in the source branch also. Now if you look at this circuit on the left and the right, these are both actually forms of the same circuit class called the common source amplifier with source degeneration. Only here we have MOSFETs instead of resistors. Now if you think about it for a minute, you will realize that the AC circuit for both of these, with of course the input at the middle transistor, this M1, if the input is here in both the circuits, then the AC circuits are identical for both these, and therefore all the analysis we'll do will be valid for the circuit on the left as well as the circuit on the right. We'll do the circuit on the right just because RDRS are more distinguishable. Here it will be just RO0, RO1, RO2. Alright, so our goal or the question we are asking ourselves is find the small signal voltage gains for this circuit both at the drain as well as at the source. Alright, and also find the output resistances looking into the drain terminal as well as looking into the source terminal. So this circuit is actually two circuits depending on whether we take the output at the drain or at the source. So we'll look at both of them. So the first thing of course we do is you pause and then you try and solve this yourself. Alright, there are a bunch of equations. So you write the equations, you solve them, find VD over V in, Vs over V in, and both the R outs, and then continue. Alright, so we draw the small signal circuit RD, RS, GM, VGS and RO. For now, I am ignoring the GMB, VBS. We'll come back to that after a few minutes. Also note that the VGS here is VG and VS. So VS is not 0 in this circuit. So VGS will have two terms, VG minus VS. Alright, so we write a KCL at the drain node to begin with. So we'll say VD over RD plus VD minus VS over RO plus GM VGS equal to 0. And then VGS is equal to VG minus VS is equal to V in minus VS. So we have two unknowns, VD and VS. So first, so usually when I solve these circuits, my habit is to once we write the KCL, I'll multiply out by the lowest common multiplier, which is RD RO. That gets rid of the fractions and it becomes an equation like this. So you multiply this out by RD RO and combine all the VD terms, combine all the VS terms. Then we'll get this equation VD into RO plus RD minus VS RD GM RO plus 1 equal to minus GM RD RO V in. So V in being a known quantity, I have taken it on the right hand side. Now the second KCL, so we're doing nodal analysis, would come from this node. So there will be three terms, but it turns out that in this circuit, if you look at this carefully, what we see is that if we write a KCL for this super node, then we'll get this equation, or another way of looking at it is to realize that this current, the current in RD, has to flow in RS also. In fact, this is the total drain current. So this current is equal to this current. So this current divides between two branches and then joins back here and flows here. So we can say that VD by RD plus Vs by RS is equal to 0 because these two currents are equal and opposite. So we write VD by RD plus Vs by RS equal to 0. So that simplifies our analysis. It also gives us a direct relationship between VD and Vs, which we'll utilize in just a minute. Okay, so from this equation we get Vs Rd equal to minus Vd Rs. And here we have Vs minus Vs Rd. So we substitute for minus Vs Rd as plus Vd Rs here, and we'll get an equation in Vd which we can solve. So we get, so I've solved it here. So Vd by Vin, there are two equal to's here. Okay, let's remove one. So Vd by Vin is equal to minus Gm Rd Ro divided by Ro plus Rd plus Rs plus Gm Rs Ro. Alright, now if we look at this, then in the denominator we have a GMRS-RO term and then this resistance is. So many times GMRS-RO is much greater than these three, and therefore we can ignore these three. And then the GMs and the ROs cancel, and so we get minus RD by RS as the approximate gain for this circuit at the drain. So at the drain we get minus RD by RS. Now you may have seen this circuit in the bipolar transistor. So this circuit of course is called the common emitter amplifier with emitter degeneration, and you may remember that the gain there was minus RC by RE, the RC being the collector and the RE being the emitter resistor. So this is the equivalent. The voltage gain is minus RD by RS. So okay, we'll come back to this in a minute. Let us find the output resistance. So okay, no, so I've written the Vs by Vin first. So we've got Vd by Vin, and then we utilize this. So we know Vs is related to Vd. So we say I want to find Vs. So it's a Vs is equal to minus Rs by Rd Vd. And Vd is known, so minus Rs by Rd of all this. So Rd cancels and this becomes Gm Rs Ro with a plus sign. So we get Vs by Vin equal to Gm Rs Ro by Ro plus Rd plus Rs, Gm Rs Ro. And so if this last term is much greater than the first three, then this is approximately 1. So that is at the source. And so this is of course the source follower gain, which is approximately equal to 1, but not quite, and we'll come back to this again. Everything we'll come back to in a minute. Alright, let's find the output resistances. So we found the voltages at the source node at the drain node. So let us find the short circuit currents at the drain and the source, and we'll find the output resistance as the open circuit voltage divided by the short circuit current. So at the drain, we short the drain to ground and find that current. Now of course when we short this, the drain voltage becomes 0. So the only voltage unknown then is Vs, and I've called this Vs1 just to recognize that this Vs of course is different from the Vs of this circuit, because when we short circuit, this circuit changes. Now this is a different circuit, and so all the currents and voltages here are different from the circuit without the short circuit. Alright, so we solve for Vs. So we write a KCL at Vs. So I'm sorry, Vs1. So Vs1 by Rs plus Vs1 by Ro, because this is at ground, minus Gm Vgs equal to 0, and Vgs is equal to Vin minus Vs1. So we get this KCL, and then we solve this for Vs1 as GMRS Ro by Ro plus Rs plus GMRS Ro. So we found Vs1. Of course we want to find the short circuit current, so we utilize this Vs1 to find the short circuit current. So this is the same expression as before, and then the short circuit current. So incidentally, so this is ground, so no current flows in Rd. So there are only two currents flowing here, and so ISC, Is short circuit at drain, can be written as Vs1 by Ro minus Gm Vs. So Vs1 by Ro minus Gm Vgs. And so we combine the Vs1 terms, and then we substitute for Vs1 from here in terms of Vin, and so we'll get everything in terms of Vin, and we can get an expression for ISCD over V in, which is this expression. And then the output resistance looking into the drain is the VD we derived divided by the ISCD. So this is VD by V in, and this is ISCD by V in, the inverse of it. Have we solved all this? And okay, so GM-RO cancels. So we'll get GM, so RD into RO plus RS plus GM RS RO divided by RO plus RD plus RS plus GM RS RO. So we recognize that this is actually RD in parallel with RO plus RS plus GM RS RO. Alright, so it is RD parallel with RO plus RS plus GM RS RO. So that is the output resistance looking into the drain of this circuit. Alright, let us summarize for the drain and then we'll do the source. So for the drain, the voltage gain, again this same copy paste has come here. So the double equal to has come. So we remove that. So the expression is, as we just discussed, approximately equal to minus RD by RS. And the output, okay, so the comment to recognize is that this gain is smaller than the gain without RS. Without RS is our traditional common source amplifier. So when we introduce RS, basically the denominator becomes larger because RS causes negative feedback. So the gain reduces, but the gain is less variable. You remember last time we had discussed that the gain of the common source amplifier varies as the bias varies because the GM varies, and as GM varies the gain varies. Here the gain is less dependent on GM, and so it is more constant than the one without RS. And so this circuit gives us more linear gain, or it is more linear compared to the one without RS. More I'm saying, it's not absolute, right? Because we are approximating this denominator to be this and the GMRSRO, which is an approximation. So there is still some nonlinearity here, but it is less so compared to the one without RS. All right. Look at the output resistance. As we just saw, the output resistance is RD parallel something. So you look at this circuit, the resistance looking into the drain is the resistance looking up from the drain, which is RD, in parallel with the resistance looking down from the drain. So our analysis tells us that the resistance looking down from the drain of a MOSFET when there is a source resistance is given by RO plus RS plus GM RO RS. Alright, RO of the MOSFET plus RS plus GM RO times RS. This is a very important expression. We keep using this throughout the semester. So it is good that you kind of get used to it. I'll keep referring to the expression from now onwards. And of course, again, one can say that this is approximately equal to GMRO RS if GMRO RS is much greater than RO and RS. All right. Okay. Now, let us qualitatively look at why RS increases the output resistance. So, of course, you can see from here that if RS is 0, then the output resistance is looking down from the drain is just RO, which we know it is the RO of the MOSFET. If we put RS, then the resistance increases. So qualitatively, why does it increase? So here is the way to look at it. So the output resistance, of course, is, so again, just looking down from the drain is VD by ID. So let's say we have, suppose we have to apply a voltage source here, I call it VD, then the current it supplies, if it is ID, then the R out is VD by ID. Now, suppose we increase that VD, the small signal VD at the drain, then we expect that the drain current would increase. But as the drain current increases, the voltage drop across the resistor RS increases, which increases the source voltage, and when the source voltage increases, the gate source voltage decreases, and so the drain current decreases. So the net increase in the drain current is smaller when we have a source resistance, because there is negative feedback which causes VGS to decrease and the drain current to decrease, and that is why the overall change in drain current is very small, and if the change in drain current is small, then the resistance is large. So that is what is happening here. Alright, so we will use this in a circuit called a cascode later on a lot. So alright, let us go back to the source. So we had derived the source, the voltage gain at the source. Now let us derive the output resistance looking into the source terminal. So we short the source terminal to ground and find the short circuit current. So in this case, the current in RS will be 0, and the only voltage we have to find is VD1. So we write a KCL at VD1. So we'll say VD1 by RD plus VD1 by RO plus GM VGS equal to 0. So GM VGS now is V in, because Vs in this circuit is 0. So we have VD1 by RD, VD1 by RO plus GM V in equal to 0. And so we solve this for VD1, and we'll get minus GM RD RO by RO plus RD, which of course is minus GM into RD plus RD parallel RO. Anyway, we really don't care about this. What we want is a short circuit current. The short circuit current is how much? The short circuit current, as we saw in the previous circuit, is the current through RD. We can write it as VD1 by RO plus GM VGS, but that is equal to minus VD1 by RD. So we just write minus VD1 by RD here, and we've just found VD1. So minus VD1 by RD is GM RO by RO plus RD into V in. So we found the short circuit current, and then we find the resistance looking into the source as the open circuit voltage divided by the short circuit current. And so all these big expressions, and then let me see, so we get this RS into RO plus RD divided by RO plus RD plus RS into 1 plus GM RO. Now if we divide and multiply by 1 plus GM RO, then we'll get RS into RO plus RD divided by 1 plus GM RO divided by RO plus RD divided by 1 plus GM RO plus RS. Now I'm able to do this because I knew that this is a good thing to do. Otherwise it is not easy to see why one would do such a strange division. Alright, but now that we've done it, we see that this is this. It is the parallel combination of RS and RO plus RD by 1 plus GM RO. Alright, so the resistance looking into the source of this circuit is RS parallel some quantity. And why is that important and useful? Because let me see, okay, here. So the resistance looking into the source can be written as the resistance looking down from the source, which is RS, in parallel with the resistance looking up from the source, which is this. So what we have found by this analysis is that the resistance looking up the source of a MOSFET when there is a drain resistance present is RO plus RD by 1 plus GM RO. And this is also an important expression. So I have put it in blue so that you will catch it and remember it. So RO plus RD, the RO of the MOSFET plus RD divided by 1 plus GM RO of the MOSFET. Which is, so if RD is 0, which is the case for a source follower circuit, then this is RO by 1 plus GM RO, and if GM RO is much greater than 1, which it most of the time is, then the RO cancel and we get 1 by GM, and 1 by GM is a small quantity. So the resistance looking up the source of a MOSFET is typically a small quantity. I say typically because it is not small if RD becomes very large, which we'll see later on. Yeah, okay. So the resistance looking at the source of a MOSFET is small if this RD is not very large. So let us put it that way. Alright, and this I am writing again, which we derived earlier. So the voltage gain from the input to the source node is this big expression, which is approximately equal to 1, as we just saw. And this circuit is a source follower. Presumably you know that the input at the gate, the output at the source is a source follower. And in this circuit, RD is actually redundant. So the source follower circuit never has an RD, it plays no role. I had included it because by including it, we are able to analyze two circuits at the same time. Alright, let's look at this more closely. So as I had said a few minutes ago, when we started the derivation, we had ignored the body effect, GMB, of M1 specifically, because M2, there is no body effect because the source is tied to 3 volts. For M, okay, I'm sorry. Yeah, so I'm suddenly changing to the circuit with transistors. It really doesn't matter, but I want to make a point here. So what we are talking about is that when we did the small signal analysis, we had ignored the body effect for this driver transistor. But of course, we need to include it. So if we include it, and I'm leaving this as homework to you, if you include it, then you will find that the voltage gain from Vs, from the gate to the source, is GM Rs RO by RO plus RD plus Rs plus GM plus GMB Rs RO. So we had not included GMB, so this is what we had got was without GMB. If we include GMB, this is what we get. And now, even if we assume that this last term is large compared to the first three, then we ignore the first three, then the RSRO cancel and we'll get GM by GM plus GMB. Now for typical numbers and ratios of GM and GMB, this turns out to be about 0.7 for basically all IC MOSFETs, roughly of this order. GMB cannot be made very small, it is just the construction of the MOSFET. And because GMB cannot be made small, GM by GM plus GMB cannot be made close to 1. And so the source follower circuit in a realistic technology has a gain of 0.7. So this is a major difference between a MOSFET source follower and a bipolar emitter follower. The bipolar transistor doesn't have the equivalent of a body, and so there is nothing to reduce its gain. So the bipolar emitter follower gains can be made extremely close to 1, like 0.98, 0.99 is common. For a MOSFET, it is very, very difficult. You get about 0.7, and this therefore has limited the use of source followers in MOSFET circuits. Now, of course, if you are thinking, you will ask the question, well, why not make VSB 0 by shorting the body to the source? If you short the body to the source, then of course VSB is 0 and GMB VSB doesn't appear, and we get back the earlier expression we had derived. So let us look at this from a layout perspective, and for that reason I have drawn these 3 transistors. So let us say that we have designed this circuit and we short the body to the source, and we did a DC analysis, and it turned out that the source voltage was 1 volt, just some value, it doesn't really matter, but I wanted this to be let's say a 1 volt. So if when we were to lay this out on a chip, so we'll have the 3 MOSFETs, M0, M1, M2, and this is the p-type body. Okay, so now I should talk about the body connections, right? So okay, so on a chip or an integrated circuit, these are called planar integrated circuits because all connections to the circuits are made at that on the top plane. So this is the top plane of the chip, and all connections are made at the top plane. There is nothing connected to the bottom for reasons that are too complicated. If you want to ask, you ask Professor Madhav Rao, he knows much more about these things. I can explain to you, but maybe if you are interested, we'll do it in the class. But for now, so what happens is, when we want to make the body connection, right? So I had said that the body of a MOSFET of an NMOS is typically connected to the lowermost potential in the circuit. So here it will be connected to ground. So this is a p-type body. So what will be done is, there will be a lot of p plus regions created across the chip on the top, nothing at the bottom. And that p plus, so for example, the M0 has a p, and that p will have a p plus body, and so there will be a p plus connection here that will be grounded. Alright, so that is how the body is grounded, by putting a p plus and grounding that p plus. Alright, now what we want is, we are saying here that for M1 I want the body to be connected to the source, which is N plus. So the way we'll do it is, we'll have a p plus for this M1, and that is my body connection for the M1, and that is connected to the source, which is N plus, and these two are connected together by a wire effectively, and that for our circuit is at 1 volt for the circuit we have designed. Now let's think what happens. This 1 volt is this 1 volt here, and this p plus is basically a short circuit. The reason it is made p plus is because on top of this there will be the metal contact, and the metal makes a much better contact to silicon if the region is p plus. That is the reason they are made p plus or N plus. A very heavily doped region makes a better metal contact. Again, this is all physics, so we will not discuss this further. But anyway, so this is 1 volt. So this is making the body 1 volt, because a p plus p is basically a short. Now I have not drawn this, but there will be another p plus here for the M0, and that will be connected to ground, because we are shorting the body of the M0 to ground. So you have 0 volt here, and you have a 1 volt here. So what happens? 1 volt, and this is just a piece of resistor, and so a large current will flow across this resistor in the body from the 1 volt to ground, and there will be a ground for here it won't happen, but another thing will happen. This is trying to make this body 1 volt. There is an N plus here, and that is grounded. So this PN junction is getting forward biased with a 1 volt on it, and so that causes a very large current in the body, which is, of course, all this is just here on this slide. For this reason, all the MOSFET, NMOS transistors in this p-type body have to be connected to ground. No MOSFET, you can't have a p plus p region here that is connected to 1 volt. It will cause all kinds of crazy currents to flow throughout this p region, which is not acceptable. Alright, so let's go back to this. So we say, well, this can't be done, but then I say, okay, well, I can't connect this MOSFET body to this MOSFET body, but can I create a separate well only to fabricate this MOSFET? So all the other MOSFETs will be in this p-type body, but because I want to connect the body of this MOSFET to some other voltage, I'll create a separate well. So you know there are wells that are created in the IC to fabricate MOSFETs. So can I create an exclusive well for this M1? The answer is theoretically yes. Technology does allow that a transistor can be fabricated separately and exclusively in its own well, and then that well can have whatever voltage one wants. The disadvantage is that creating a well for a MOSFET for itself is very, very expensive. Chip area is very expensive. And so if one MOSFET occupies a very large chip area, then the cost of the circuit goes up. And therefore, this is done only if there is justification for having one MOSFET occupy such a large area. If the cost is justified, then one makes a well for a single transistor, and usually the cost is not justified. So I would say out of 10,000 times, maybe once such a cost is justified and it is done. But for our purposes, we'll basically assume that source followers are not very efficient in MOSFET circuit. Okay, this lecture has become already more than 30 minutes, so we'll do the diode connected load in the next lecture. We'll end the lecture here.